Hello and welcome back to Precalculus1. We are going to talk about exponential functions, which are some of the most important functions in the galaxy. They model so much of everything you're ever gonna do that by the time you're done with your STEM, one function you'll be sick of is exponential function because it's literally everywhere. In 3.5, which is the section on word problems and applied stuff, which is the most important, you are going to see that exponential functions are used in history for carbon dating, right? So you're talking about archaeology and history and all that stuff. Then you can use the exponential functions in economics and business. You can use exponential functions obviously in engineering, so electrical, mechanical, and everything else. Used in physics, used in chemistry. It's literally everywhere. Exponential functions will be everywhere. So this section is extremely important. Your later courses will be using exponential functions extensively, right? Especially calculus and so on. So let's talk about exponential functions and see what they are. So the first order of business over here is to see what is going on with definition, right? So we have b to the x, right? That's some basic idea. So this is going to be our base, and this is going to be our exponent, which has x in it, also known as power. So when you say 3 squared, well, that is just 3 times 3 equals to 9, and this is not exponential function. Right? Function requires an x. So when you say 3 to the x, that would be exponential function. So we have to make that clear first. Before we do anything else, we have to make clear that when you say 3 squared, or if you go, I don't know, 5 cubed equals 125, that's just arithmetic, right? You're just computing 5 times 5 times 5, you get 125, you're done, right? So that's all it is. But if you have 3 to the x or 5 to the x, so on, then you are getting what we call exponential function. So I would like to first learn the properties of exponential function. So exponential function will be written as f of x equals to some base raised to the x. So that's our main expression here, where b is the base, x is the exponent, and that's where the variable is. And we know as you change the variable, you change the values and the outcome of the function. So what do we want to know about function? And the answer is everything. We want to know domain, we want to know range, we want to know what the graph looks like, we want to know x-intercepts, y-intercepts, we want to know to graph it by hand and shift it around and reflect. Literally, we want to know everything there is to know about this function. And that would be prerequisite knowledge that you will later on use in calculus courses and other courses to describe pretty much almost everything, right, that you will be dealing with. This chapter is insanely important for your future education. So let's take a look at the graph, and then from the graph we will be able to determine a lot of other stuff. So graph. Now let's use our good old middle school technique, right, where we assign x's and compute y's. So x graph, y equals 2 to the x, standard. And what I'm going to do is I'm going to have a couple of these values that we can compute. So -3, -2, -1, 0, 1, 2, 3. That's enough. From -3 to +3. And then we're going to have our XY coordinate system, where we are going to draw all of those values, X and the Y. Alright, so first value to compute right here would be 2 to the -3. Now, we cannot compute negative number in the exponent. Luckily, algebra is going to kick in and help us with calculating this. So that is, using algebra, 1 over 2 cubed. And 2 cubed is 8. So we have that the first value is 1 over 8. Alright, so now we'll have to use more algebra. So when the number is -2, then that's 1 over 2 squared. 2 squared is 4, so 1/4. Then when the number is -1, that's just 1/2. Then value raised to the 0 is going to be 1. So all I'm doing, I'm computing these values using basic algebra, arithmetic, whatever you want to call it. Then 2 to the 1 is 2. 2 squared is 4. And 2 cubed is 8. And all I need to do is to graph these ordered pairs x, y, and then connect the dots. So what I'm going to do is have my divisions from -3, right, to +3. And then, as you can see, there are no negative numbers on y, so I only need 1 through 8 on the, 0 through 8. So 1, 2, 3, 4, 5, 6, 7, 8. And I can go and plug these values. So let's use red for points. 0, 1, that's on y-axis. And let's do the now negative values. So -1 gives us a half. That's a half a line, a half a square over here. Then it's a quarter. Then it's an 8. So as you can see, it's getting closer and closer and closer to x-axis. And the spoiler here is that it will never touch x-axis and it will never cross x-axis. On the other side, 1 goes with 2, 2 goes with 4, 3 goes with 8. So if we draw the line through these points, we would see that that line will come here from all the way from -infinity, and it will shoot through all of these points up to +infinity. What we see is that the end behavior is as x goes to -infinity, y goes to 0. As x goes to -infinity, y goes to 0. On this side, end behavior is as x goes to positive infinity, y goes to positive infinity. And it's rising very quickly. Remember that your linear growth, I'm going to erase this, your linear growth would go like that, like this, right? It doesn't grow as fast as exponential, right? So you probably heard before, oh, it's the exponential growth, when something grows quickly. The virus spreads exponentially. What does that mean? That means that small amount of people are infecting the large population. That's why all of the models that we are using are exponential logistics models for spreading the virus, or for spreading the computer virus, or population explosion. There's a lot of stuff that we right, medical field. And then we'll also see that metabolizing drugs in the body in terms of medication and so on, all exponential. Then you have environmental concerns like radioactive decay or garbage decay. All of those problems are exponential. As I said, technically every aspect of your life is in some way, shape, or form governed by exponential function, including the battery charging in your for your cell phones and so on. They have exponential for the circuits and so on. So there is a lot of stuff. Exponential functions are everywhere. So now what we see here is we see basic b to the x, where b is positive, right? If b is negative, then we have different situation. But now we're just looking at this. So end behavior tells us that on the right hand side, for the standard case exponential function, as you go out in infinity, you go and as you go in infinity in x, you will go to infinity in y. Now what I want to do is take a look at all other aspects of this. So what is my domain, right? We are always concerned with domain in pre-calculus, and you can see, since domain is all x values that you are allowed to plug in, you're allowed to plug in anything, right? There are no vertical asymptotes anywhere. There are no interruptions. So domain is negative infinity to positive infinity, because we are allowed to plug in any x value into this. Now a range, which is the set of all y values, is going to be 0 to positive infinity. We are not including 0. We are not including 0 like this, because the graph will never touch or cross x-axis, right? So we do not get to reach y equals 0 ever. Therefore, y equals 0 is not the part of the range of the function. Well, we also want x-intercepts, and that's none, because I just said it will never cross x-axis. Well, therefore it can't have any x-intercepts. That should be common sense. And finally we have y-intercepts. Now y-intercepts, for y-intercepts, we are going to have, in the original case, we're going to have it at 0, 1. And you can see that y-intercept right here, right? That's the y-intercept where the graph cuts through y-axis, therefore y-intercept. Cool. No symmetry on the graph. Some graphs, as you've seen before, some graphs have symmetry. I will just go on the side over here, show the symmetry for x squared graph, right? There is a symmetry right there. If you draw x cubed graph, it's symmetric on y equal x line. So there are certain symmetries that we can have in right, in mathematics. This one has no symmetry. There is no line that you can place so it mirrors. If you try to say, well, we can just place a line here, no, you can't, because there is no asymptotes. This will forever go this way, and it will forever go up. So therefore, you can't put any kind of vertical barrier and then try to have a symmetry line. That doesn't work. No, right? It's not for exponential function. Exponential function. So this is so we have a whole bunch of these functions will go forever, right, to the left and to the right. We can use -10, we can use -1,000,000. Then we have a positive values. We have a positive value of 10, right? You can calculate 2 to the 10, right? It's going to be somewhat larger number. I mean, not large at all. I mean, what do you have? 2 cubed is 8, then, so 16, 32, 64, 128, 256, 512, 1024, nothing, right? 2 to the 10 is 1024. That's nothing. Now the numbers are going to keep growing quickly because every time you compute the next value, you're doubling it, right? But the idea is that it grows quicker than any polynomial. So now we have domain, we have range, we have x and y intercepts, we have no symmetry, right? And we understand the graph to some extent. Obviously, we're going to do much better job with graphing these. Now, you might ask after this, well, okay, but you said 2 to the x. What about 3 to the x and 4 to the x and right? Well, what's happening here is just the line is going to either grow quicker or it's going to grow slower, right? And the best way for us to explore that is to actually go on Desmos and graph a whole bunch of these lines. Now I'm going to draw a quick sketch, which will be terrible, but I still need to do it. So I'm going to draw a quick sketch over here on the side so we're all understanding what's happening as we have, right, with the shape of the graph. So if I say that this is my shape of the graph for, let's say, 2 to the x, then I might have a graph that it's going to go like this. And that's maybe 3 to the x. And then this one maybe to be 4 to the x and so on. So what's happening is, and I'm going to actually, do a much better job when I open Desmos now, and well, Desmos will do a much better job. I'm just going to attach the keyboard real quick and jump to Desmos. Desmos.com, there we go, start graphing, and here is our 2 to the x, right? And you get this red graph, and you see it looks exactly the same as the graph that we had. Now for the next function, right, I'm going to have 3 to the x, and as you see, right, it moves a little bit closer to y-axis because it grows faster. And then we are going to have 4 to the x. And as you can see, it's even closer to the y-axis because that one grows even faster, right? So it is not humanly possible to do absolutely amazing job on these graphs and so on. Close enough is close enough. We just want to know that, we have this curve, that it's a general shape. All of these shapes look the same. They're just which one curves faster, right, grows faster, and which one grows slower. And unless you really dig in and, show off all of the points, you are not going to do the most amazing job right, to these. So here's 1, 5 to the x also, and I'm going to stop right there, right? So that was the purple one all the way in, right, closest to the axis. So the more of these you draw, the more it will happen. Now the next one, it says there was a question asking if we can have a polynomial, right? Because you probably already figured out that x is just a linear, right? Linear x. And can we have e to the x squared or e to the x squared plus 3? And the answer is yes, we can, but through function composition. And that is coming a little bit later, right? Right now, we only care about the basic state of the function, which is e to the x. And once we jump into, function composition and other things, then we might see some of those more interesting cases. If you took statistics, or if you are taking statistics right now and you have heard of the bell-shaped curve, since you asked, this bell-shaped curve, that bell-shaped curve has some kind of formula of e to the negative x squared, right? So yeah, you can have these kind of things, but the shape of the graph will be, different, and so that's not going to be something that we are considering here at this moment. So we know basics of our exponential function now, right? We know that it has all real numbers as domain, only the upper half of the plane for the range, no x-intercepts, one y-intercept, like every other function can only have one y-intercept, and no symmetry of any kind, and all of the graphs will look like that, right? We'll see that they also can go the other side when you reflect them, but that's what they all look like. And then as you have higher base, they tend to grow faster, so they go closer to the y-axis because they grow faster. Okay, now it's time to take a look at the partner in crime, which is exponential function for the negative exponent, right? So what happens, right, to our graph if we have negative exponent? So what if I have y equals 2 to the negative x, right? And this one, we don't have to go as much the detail as the previous one, so I can just go from negative 2 to 2, right, in interest of time and sanity. And now when you put negative and negative will make a positive, so that's going to be 2 squared, which is 4, and then 2, and then 1, and then 1/2, and then 1/4. So you see that all of the numbers are flipped. And because the numbers are flipped, right, our graph, if all of the numbers are flipped, then our graph is just going to go the other way. So now, I'm going to use now 2 squares as 1 unit, because we can. What? No, I can't. Fine. You win. Alright, so I have negative 2 gives me 4. 1 gives me 2. Then I have 0, 1. Then I have my half. Then I have my quarter. And as you can see now, this is what we call, and we'll use it a lot, which is what we call decay graph. So when the value is negative, we call this decay graph. This is the graph that will show decay of radioactive materials, decay of garbage, decay of carbon C14 for carbon dating for your anthropology and for archaeology and history and so on. So a lot of decay problems can be solved, and also decay would be used to dampen the motion, so that's why the pendulum stops, right? If you stop pushing kid on a swing and the kid is not swinging their legs, then the kid will eventually stop. Or if you just make any kind of pendulum and just, whack it and you just leave it, it will eventually stop. It stops because of the e to the negative x number, and those things are explained later in physics and so on. So very important function. And again, can you have a negative 3 to the negative x and 4 to the negative x, and all of them are just going to be more aggressive, right, as they come in, right? They decay faster. But the most important part to see over here is that it never goes away, right? The y values will never reach 0. X would go into infinity and they would not reach 0. And that will have some very interesting points later on that we will discuss once we reach 3.5. So we have the decay, and the best way to describe these functions is to say y equals b to the kx. And I love this kx because the k, when k is larger than 0, we have growth, and that's the graphs that grow quickly. And when k is less than 0, we have decay, and that's going to be our, right, going to 0 situation on the graph, right? So those are the values. And now I could add, I don't want to do it now, but I could add also a in front, right? And that would be this a, you will see later, is just going to be flat out, it's going to be the y-intercept, but we'll deal with that when it's time for it. So this is a really cool thing to know, right? Cool thing to know. And as you can see, for all of these, you have the same spec. Whether it's a decay or a growth, you have that the function has all real numbers as domain, upper half as a range from 0 to infinity, no x-intercepts, and only one y-intercept at 0, 0, 1. So those are our basic specs of exponential function. And what do we want to do with this? Well, we definitely want to learn the graphing. We want to shift it left and right and up and down and so on. Well, one thing that we need to understand here is that, remember how, see, this goes to infinity this way, this one goes to infinity this way. Well, now it's time, when we want to talk more about graphing, to talk about horizontal asymptote, right? So I will write here that exponential function has one horizontal asymptote at y equal 0 for basic case, right? B to the x or b to the negative x. So there is a horizontal asymptote that is actually the x-axis in this case, and there are, I'll just for the sake of it, I'll say no vertical or slant. I shouldn't be writing slant because by now, if you studied at all 2.6, you know that if you have horizontal, you cannot have slant. You should know that by now. But let's write it because it's infinite ink, I guess. I mean, until the battery runs out. All right, let's take a look at graphing. Now, when I say graphing, I mean 1.6. I did tell you that sections 1.6, 1.7, and 1.8 will never go away until you are taking STEM courses. Not math, just math, but any STEM course, including physics or any kind of engineering, chemistry, whatever, right? So if you're taking any STEM course that has any mathematics in it, sections 1.6, 1.7, 1.8 will never go away. Anytime you learn a new function, sections 1.6, 1.7, and 1.8 will be there. So now section 1.6 for exponential function is just going to be graphing and shifting it everywhere. Then we're going to have the function composition, right, where we are going to combine that with other functions. And then eventually we are going to have the inverse of the exponential, which is 1.8. Inverse of the exponential will be logarithmic function, right? So those three sections will be repeated for logs, will be repeated for trig later on in Precalc2, and then you're just going to use them pretty much every day when you start your calculus courses, all three of them, and diffq too, right? So those sections never go away. And now we are going to apply concepts you learned in 1.6. You're going to apply those concepts on this on these examples here. So let's see. First off, if I have f of x equals 2 to the x plus 3, right? So when you're looking at this particular problem, you see that this is of the form f of x plus c, right? And we should all know what this plus 3 does, right? Because you studied 1.6. You only care of the form. You don't care what function do you get. Plus 3 does everything the same for every function, right? As long as it's plus 3 added to the whole function, it does the same thing everywhere. So what did the plus 3 do before? It has to do the same thing now. What did it do? It shifted up 3 units. So plus 3 over here is up 3. That's all it is, right? Because plus c means up c. That's all it means. So you learned that in 1.6, and as I said, it stays the same forever. So now to draw your graph, right? You put your x and y axis. Remember, we don't need much under the x because I'm raising this up. Now I had my horizontal asymptote at x. That needs to go, right? Because I'm raising 3 horizontally. So I'm going to now go at 3, and I'm going to put my horizontal asymptote now at 3. Because it used to be at 0 and needs to raise up 3 units. So now I have my horizontal asymptote there. What used to be a point over here at 0, 1, now that has to go 3 units up. So now it's at 0, 4. And the whole graph just shifts up, and we just draw the shape, right, for exponential function, and we're good to go. It doesn't have to be amazing drawing, but you do have to write number 4 right there, and you're done. Woohoo, right? Can we shift down? Sure, just put -2 and put the blue line at -2, right? And then you're done. Can we shift left and right? Yes. Say you have f of x is equal to, 3 to the x plus 2, whatever. See, now plus 2 is attached to x, right? It's not 3x plus 2. That's up. This plus 2 is left. Again, all of the same principles that you guys learned in 1.6 are still applied the same way here. So if you have the f of x plus 2, or actually use the c, right? Then that means it's moving to the left. Okay. Draw the XY system. We have our horizontal asymptote stay where it should be, which is the x-axis, and our good old y-intercept point has to move 2 units to the left. So it moves right here, and you just draw the shape. Obviously, we're going to have a new y-intercept now, but it's still exponential shape, right? Exponential shape graph. That's the exponential shape graph. And it goes somewhere through the y-axis. Now, because we had to move it to the left, because that's what was asked of us, right? We have the y-intercept show somewhere else. Now, you have to note that this point over here is negative 2, 1, right? Because that used to be your 0, 1 y-intercept. Now y-intercept will have a new value. So I'm going to add that here as a note. We have new y-intercept set x equal to 0 to get it. So x equals 0, we have 3, 0 plus 2, which is 3 squared, which is 9. So it's 0, 9 for our new y-intercept for exponential function. You know, your x-intercept is found the same way like you find it in algebra, in anywhere, right? Any function calculates y-intercept the same way. Y-intercept is always x equals to 0, because when you look at the x-axis, x is 0 on the y-axis. So it makes sense, right? Common sense, to plug in x equals 0 to calculate y, because you want to know how high or how low y value is when x is 0. Because y-axis is where x is 0. And we still don't have any x-intercepts here. Now, is it possible to get the x-intercepts? Yeah, just shift the function down, right? If we shift the function down, we are going to create x-intercept. We might not be able to compute it, but we can at least know that it's there, and then in the coming sections we will be able to compute it too. So say f of x is equal to, right, graph still, f of x equals to, I don't know, 4 to the x minus 2 plus, no, minus 3, whatever. So what do I have? I have 2 of these now. This one is down 3, and this one is right 2. So we graph them. You can do it in stages, or you can do all at once. Let's see if all at once is a mess. So I'm going to draw, I don't know why I'm suffering with this when I can just, because I practiced this shapes, as you can see. So I have my y, have my x. So down 3 units. Down 3 units means my horizontal asymptote goes down 3. So that's my -3. And then my intercept should be here, right? But I need to go 2 units to the right, because we also have a horizontal shift. So the graph will come in. The graph would come in following and then shoot to this point and whoa, create X-intercept as well. So now, new X-intercept. Get it by setting y equal to 0, which again makes sense because if you're looking for this point, that point is on the x-axis. Y is 0 there, right? So we don't know how to compute this thing yet, but if I set y to 0, I get 0 equals 4x minus 2 minus 3. So 4x minus 2 equals to 3, right? And now we're a little bit stuck, right? We're a little bit stuck. So need to learn, right, the way to solve exponential equations. And that is in 3.4. So we wait for 3.4 lecture to solve this and get our X-intercept. Right, sometimes it's easy, right? Sometimes it's easy. But, and we can do it without 3.4. This one we need 3.4, right? We need it. I'm going to erase this. I'm just going to put this because this is, you know, just a very simple, I would say, common sense thing. If you had 4x minus 2 equals to 4, right? This one doesn't require any special witchcraft, right? You can just compare two sides. Because see, this is 4 to the 1, right? Because bases are the same, and you have the same base, then that means just x minus 2 equals to 1 and x equals to 3, right? It's very simple. But again, we don't have a 4 over here, we have a 3, so we can't do this, right? We have different bases. So when you have different bases, we have to deal with that using 3.4. So we'll wait. But for some simple cases, right, you can definitely do it by hand. And maybe some of you already know how to punch these things in a calculator and get the value without, right, worrying too much. Okay. So now we understand that. I want to also toss in the reflection, which is important. You know, let's say you have your f of x equals, 3 to the negative x. You say, that's easy. We learned that's a decay graph. Yeah, but it's also a reflection of the previous one by on the y-axis, which is what we learned in 1.6. So if I look at this one, it's exponential decay. If I look at this one, it's exponential growth. What happened here? What is different between the two? What's different? It's reflected on y-axis. Well, that's exactly what you learned in 1.6. Section 1.6 says that when you have f of negative x, we reflect on y-axis. So there is no surprise there. All of mathematics has to click everywhere, right? There are no exceptions ever, anywhere. All of it has to click 100% of the time, right? and no inconsistencies of any kind anywhere. So the rule you learned in 1.6, now you might just give it a different name, but it's still the same rule and it still has to 100% fit everything we are learning. So your decay and your growth graph are just simple 1.6 reflection of each other when you change x to negative x. That's all it is, right? Now you can put a negative in front of the whole function, and if you put that, that's going to reflect it on x-axis the same way you were expecting. So if you have f of x equals to negative 2 to the x, right, then by 1.6 it is reflection on x-axis. So in that case, the graph would look like this, going through negative 1. Because the original graph did that. So that's 2 to the x, and this is negative 2 to the x. Again, not to be confused to 2 to the negative x. 2 to the negative x is decay. This is not decay. My decay needs to drop down and approach infinity, right, as it drops down to 0. This one just plunged down to 0 immediately. It just went, face down. All right. So the next order of business is for us to take a look at the function, exponential function, with a very, very, very special base. All right. So we are going to see the very, 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 very special base. This is the one that will be used pretty much everywhere. And this one is going to earn the red title, all capitals, screaming off of the screen, the natural base E. Lowercase e, it's Eulers number. I did mention Euler a couple of times already in our course before. He was one of the gods of mathematics, probably the most effective and most productive mathematician of all times. Most of the mathematics we know today, right, came from him, including exponential, logarithmic, trigonometric stuff, and all of these things that you learn. So he basically laid a foundation for 80% of your pre-cal course across the board, and then all of the complex stuff. And I mean, he was just absolutely amazing. And the number E is in honor of his honor. The Euler is spelled with the E. It's E-U-L-E-R, Euler. And this number here is basically going to be your cornerstone of all of calculus. There isn't a lecture, right? If I go back and poke into any calculus lecture, they're all going to have E's. If I poke into differential equations, they're going to be E's all over the place. Base E, which is the natural base, is used everywhere. And then there are some notable examples where you are not using base E, and we're going to cover those as well, but very little stuff is non-E. Pretty much everything is E, 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 E. So, first of all, E is this very strange, irrational number whose decimals go forever. They never repeat into a pattern, right? They never stop. So it's irrational number. and it is 2.718281845904523. I don't know how many. The book stopped somewhere in here. If you are, a nerd, you're going to remember as many of these as possible because it's cool. I know there is a 60, so there should be a 60 right there, and so on. So it goes on forever, like never stops. So it is irrational number. So the pattern there's no pattern, right? And the decimals never stop. So because of that, right, E is generally just learned as E and used as E. No one goes around, waving with, 100 decimals. But you can find, programs and so on. Now, in calculus, you learn the true definition. I am going to give that in here for the sake of completeness, but you learn it in calculus. This is not going to be on a test, right? The definition, I'll say calculus. Oops. Is E equals limit n goes to infinity of 1 plus 1 over n to the n, right? So this is the definition for the number, and we are going to actually see that this is actually what the problems are indicating, or for the stuff that we are going to do today and you're supposed to know. But we are not going to have this in this course to be something that it's important for you now. All right, cool. So what is E? E is about 1.7. Okay, sorry, 2.7. So E is about 2.7. That's it. It's a constant. So you can count 0, 1, 2, E, 3, pi, 4, 5, right? If you want to toss in important numbers in your counting routine, there you go, right? So they fall in somewhere on the number line. And now our natural exponential function is going to be y equals e to the x for the growth, and y equals e to the negative x for decay. Now, in general, what we like is y equal a e to the kx, which is much better, and then k less than 0 is decay, k more than 0 is growth. You still have the same graphs, decay, growth, and all of the specs that we learned before, domain, range, blah, blah, blah. It's all the same, shifting all the same, right? E is not going to bring in new rules. E is, instead of you using 2 or 3 or 5 to the x, you are using now 2.7, right? 1828, 1828. 459045235360, and I believe the next one is 28, and so on. So it's like a lot of those decimals going on. So we are not learning new function, we are just learning the special case, which by doing the science in nature, which we understand that it's the one that models the world around us. And now we can think about where this E, kicks in. So let's talk money a little bit, okay? So loans like credit cards, like student loans, car loan, right? any type of a loan. Mortgage is a little bit different, but to some extent mortgage as well, right? So pretty much loan of any kind where you are going to have the interest, right, the rate, the percent. So you have P to be principal. That's the money borrowed or money borrowed, let's go that way, because you borrow money, right? R, it's going to be percent interest. We'll have better words later on. T is time, usually years, right? So we can calculate something is called compound interest. So what's happening? See, interest is the money you pay as a service to someone who lets you borrow their money so you can do stuff. You see, you go to mechanic fixes your car, you pay for the part, you pay for labor, for mechanic's time and knowledge to do it. You go to hotel, you pay for the service called the room. You also pay for room service. You pay for a busboy to bring your bags. Maybe you don't. I don't know. But the thing is that, right? You always pay for service, right? No matter where you go, you in a restaurant, you tip a waiter because it's a service, right? So when you borrow money from a bank or someone who has a pile of money, you pay them a service that it's called interest. And usually, right, that interest is low. In case of, if you are comparing it to other services, and everyone is screaming about interest, which I will never understand, because if there was no institution of interest, you would never be able to borrow money and buy stuff that you cannot afford with the cash you have at hand. So I never understood people bitching about interest. Interest of 4%, right, means that every month, right, that you didn't return the loan, 4% is added to the pile you owe. Right? We'll do the mathematics of that. When you go and you buy, you go to a restaurant, you leave 10, 15, 20% tip. So what? You left a 20% interest at the restaurant to buy, stupid dish of pasta that you can make it at home for like $2, and you left 20%. Where you borrow the money to buy a car, which you need to survive, all of a sudden you're bitching on the interest. There was 2, 3, 4%, right? That never made sense to me. Why are people like that? But whatever. So compound interest is something that you are adding on top of the payment as a service to those that are lending you money. So when you swipe a credit card, and it charges interest because every time you swipe the credit card, you borrow the money from the bank that issued you the credit card. Now, that's not a debit card. Debit card is using available money on your bank account. That's different. I'm talking about the credit card that, you have allowance of $1,000 or $10,000 or $20,000 on it, right? Or the infinite amount if you have one of those black cards. So that money is not yours. That money is bank's money. And then what you do is you swipe the card and you technically set the bank, I'm buying this pack of gum for $3.50. I don't have cash. I'm swiping the card, so I'm borrowing $3.50 from the bank, and boom, you have to pay 2% interest, right? Because you borrowed money. Now, obviously, if you paid that, cash, then there will be no borrowing and there will be no interest because you paid with your own money. But because you swiped the credit card, you borrowed the money, and then there is interest because that's a service payment, right? Because they lend you that money for you to use. So interest is percent that we convert to decimal. So let's say that you have a credit card and generally all the credit cards, are the same. Basic credit cards for people that have, somewhat okay credit score and so on would be, let's for simplicity, 24% APR, which means annual percentage rate. So you divide that 24% by 12 months and you get 2% per month. So if you charge $2,000 in a month, you owe back $2,000 you spend plus 2% of $2,000. So that's $2,000 plus 0.02 times 2,000, which is 2,040, right? Because 2 times 20 is 40, and you add that to the 2,000. So this is how much you owe. So $40 is the service that you are paying because you borrowed $2,000 which you didn't have. I don't know. You had to fix the car, you had to buy a new computer, or you wasted it on expensive clothing and shoes or whatever. I don't care where the 2,000 went. The point is you didn't have it. You borrowed that money. And because you borrowed that money, interest kicks in at 40%. Now, obviously, this all gets much worse when you go to those companies and buy and open the store cards, right? Like Macy's and all of these retailers that are actually having 30, 31, 32% APR. And then when you divide it, it's much more than 2%, which are the regular credit cards. If you ever want to have any money in life, never, ever open any retail card, because they're going to tell you, yeah, open our card, save 10%, but then they hit you with 32% interest on it. So, yeah, who's an idiot there? All right. So now we see that the amount is equal to principal plus principal times the percent rate. So A is the amount that you owe, right? And you can factor out the principal and you get 1 plus R. Now, this is what you have going into the next month, let's say. So the amount you owe next month will repeat this and add another one of these. So if I call this A1, then A2 will be principal 1 plus R squared. And then A3 would be 1 plus R cubed. And it would go like that, all the way through A12, let's say, where you are going to get your to the 12th power and so on. So compound interest, obviously if you're not making payments, it is accumulating, and then there is bigger and bigger and bigger pile of money that you owe back because you were not paying off the service. So now what's happening there is we are able to create a formula, right, for this, where you are computing. I'm going to write it and then explain it. There we go. You have the formula now, which is called the compound interest. This is the formula you will be memorizing to do money problems. And you have your A as the amount, P as principal, R as rate in percent, convert to decimal, T is time, usually in years, right? You borrow money for a couple of years, 3 years, 5 years, 7 years for cars, right? You take a student loan, 10 years, right? Your investment in education, if you don't have scholarship because you never participated in any activities and you can't apply for scholarship. So all of these kind of things, right, are there. And then there is this N. N is the number of compounds per year. And I'm going to say that N equals 12 for credit cards, car, student loans, because you're paying every month. But you can compound twice a year, then N is 2, 4 times a year, right? Once per season, that's quarterly, right? You can compound weekly, you can compound every hour, you can compound every second, you can compound every millisecond. You can be compounding this, but what's the most interesting thing is that the upper limit of all of your compounds is going to collapse on this function E. So we can have N equals anything, as long as N larger than 0, right? N equal to anything, right? Then it's a whole number. So larger than 0 and whole number. And that is equal to the number of payments. Well, I already said that, number of payments per year. Well, let me write it that way. Number of payments per year. See, number 12 is a very nice number. It's divisible by 1, 2, 3, 4, 5, no, not 5, 6, and then 12, right? If you really want to create a bank that it's really annoying and in collection of money and all of that stuff, just have 7 compounds, right? So you divide 365 days by 7 and you say, okay, we're compounding every month and something, right? So the idea is that you can compound on anything. So let's take a look at the situation with a loan. And then we'll kick in with E at the end. So loan. Let's say you're borrowing $6,000 for a car, right? $6,000 for a car, which you don't have, at 4%, on 5 years. Or, I don't know, do you want 3 years, 5 years, whatever, right? Doesn't matter. We can actually use this to compute the monthly payment. And by the way, this is what is used to compute your monthly payment. However, I mean, I know there are those online calculators and blah, blah, blah. This is what's programmed in. Now, the thing is that this is not the real price. If this is a sticker price, you have to add 7% tax. You have to add all other fees, right? When you're buying a car, you have a deed, you have insurance, you have registration, you have like a whole bunch of stuff. So it's going to be like, $8,000-9,000 to buy a $6,000 car. This is just a sticker price. You still have to add the tax. You have to add all of those things. I mean, tax on this thing is $420, right? So plus $420 just for the tax. So you are going to do this on 8,000 actually if the sticker price is 6,000. But let's not worry about those details. Let's say you need to borrow $6,000 for a car, and then these are the specs that are given. So what do I have? Well, principal is 6K. That's what I'm borrowing. My rate is 0.04. My time is 5 years, right? And I also know, because I live on this planet, that n is 12. That's something you just know, because you will be paying this car every month, right? So, since you are making monthly payments, they will be compounding interest every month on the amount that is left to still pay off. So, n is equal to 12. And how much do you owe back? Right? How much do you owe back? Well, A is equal to P 1 plus R over N to the NT. You memorized the formula. And the amount you owe is $6,000 times 1 plus 0.04% divided by 12 raised to 12 times 5 years. Now it's time to take your calculator and calculate how much would this cost. I see $20 per month. $20 per month for this car I'm not talking about renting, I'm talking about buying. So let's see. So 6,000, 1 plus, and I am now dividing 0.04 by 12. Right, so make sure you have your calculators and pay attention to the amount of decimals I'm keeping around, otherwise you're doomed. So 0.00, and then I am going to keep 4 significant decimals here. We call that significant digits in STEM. See, these zeros are not, right, these zeros are not significant. But these are the digits that are significant. So I am not keeping 6 decimals. Sometimes there's going to be 7 decimals, sometimes 5, sometimes 4, right? We just want 4 non-zero numbers. That's what is important. So now we have that A is equal to 6,000. 1 plus this number is 1.003333 raised to the 60. Now, next by PEMDAS is to raise this number to the 60th power. And we keep 4 decimals again. So it's going to be 6,000 times 1.22099, so 1, and then the next number is 0, but we don't need to write 0. And then I multiply that by 6,000 to get that the money that we owe back is 7,325.98 Now make sure you keep 2 decimals for cents. Let me write that in blood, because sometimes I read the exam and, the money owed, and it gives me like 7 decimal places. No, it's cents, 2 decimal places. So 4 significant digits in decimals when you are computing, and if you are dealing with money, 2 decimals because cents, right? So need 2 decimals because money has cents, right, as decimals. Dollars, right? All right. So this is how much we owe. This is what we owe back. So what's my monthly payment? It's going to be this divided by 60 months that we have to pay it back, right? Because we will be paying it off 5 years. So you take this money, you divide it by 60, and you get that the monthly payment is $122.10. So this is your monthly payment for this car. So if you want to buy a car at 4% interest because you didn't have money, cash, right? You don't have 6,000 cash. So you are going to pay $122.10 per week. Now you understand why when you are buying a new car that it's, about 20K, why is the payment $350 on it, right? Well, roughly 3 times more, right? 6,000 times 3 is 18,000. Your payment times 3 in this case is 366. So it all makes sense, right? Some people who bought a brand new Tesla S, right? They took a second mortgage, right? Like buying a house, because they had to borrow $100,000 to buy the car, right? Now over time, right, pays off in gas costs and everything else. I mean, electricity is cheaper, especially if you're working for a company that provides free charging. A lot of companies out there have chargers in front of their company, and they're completely free. Well, in that case, you literally have $0 to pay for Tesla. Oh, it's per month, because we had the question is 122 per week or per month or it's per month, because remember, you are paying 5 years and there are 12 payments, right? So 12 times 5 is 60. We divide it by 60. So you have 60 payments, 60 months. So this is per month for 5 years. So that's what we have. All right. So what next? Right. Now we can calculate this way technically any loan you want. Now you know. But there is an easier calculation than this one to figure out. Now, it's not used by banks. It's not used by banks. This is used by banks to calculate your loans. But what you can do is you can have the easier formula with E. You can have easier formula with E to calculate your absolute maximum monthly payment, because E is that limiting value. So to get max payment, and easier formula, we can compute A equals PE to the RT. Appert. I don't know if you can do this without rolling R's, so I guess you will be practicing rolling R's. So you can say appert. Okay, so this is going to give me a larger number than 122, right? This is important to compute prior putting on shoes and going on to bargain with the dealership, because I'm going to show you something else after computing this formula here. So we're still borrowing 6K. We're still at 4%. And we're still at 5 years. Now, when I plug all of this in the calculator as 6K times E to the 0.04 times 5, you will find E on your TI-8384 calculator all the way to the right. So let me get over here TI-83 or 84, that doesn't matter. So why you kill my keyboard? TI-83. There we go. And then we go to images and pick up one of these images. Open in the new tab. There we go. So right here on the division sign, you see E, right? Not to be confused with the E symbol above sine function, right? So that's the lowercase e. And you can use that one using the second button, the yellow button up there. But there is one more E that you can use, and that's right here above this button ln. There is also e to the x. You can literally use either one of them. If you use the other one, you have to push the exponent button, which is the little caret sign above division. Or if you use the button that has ln on it, right, with the second key, then you can just push in E, right, in a single shot. So I'm going to use 6,000 E to the 0.2. So I go and I say second division, put caret, and then 0.2, and that should give me 1.2214. And now when I multiply that by 6,000, I get 7,328 and 42 cents. Now, as you can see, it's about $3 more. Oh, come on, right? $3 more on a 7,300, right? Don't worry about it. So, but it was much faster to compute and easier to remember, except you just have to have the calculator with the E. Now, cell phones do calculate this when you flip it sideways. Even iPhones can do it. So you can just, flip it sideways and get the E function going. The last thing that I want to talk about before we leave for today is the famous win-win situation, right? For everyone. When you say, oh, I can't afford, $122 a month, can you work on me on a price? and they say, well, the online listings are the cheapest listings you can have, so we cannot move to the price at all. But if you want to, pay the car on 7 years, we can get you better rates, so your payment will go down. Aha. Let's check that. Let's have the same problem of you're borrowing 6K at 4%, but this time 7 years to pay it off, right? You will see that your payment is going to be significantly lowered, right? Now, we also need to understand why everyone wins, right? So let's see. So we have our principal, our A is equal to the principal, which is 6K, 1 plus, we have our 0.04, which is the R, divided by 12, that doesn't change. And now you have 12 times 7, because now you're going for 7 years rather than 5 years. All right, that's 6,000. 1 plus, this number doesn't change from before, so 0.003333, and now over here you have 84. So now you have 84 months payments rather than 60 months, right? Extra 2 years plus 14. So this is going to be 6,000, 1.003333 raised to 84. Now you raise the number to 84 first, then you multiply by 6,000. I'm doing everything in one shot to get that the amount you owe is $7,934.86. So now your monthly payment is $7,934.86 divided by 84 months. And that works out to be $94.46. Hey, you just knocked off $25 off each payment. $25. So the dealer will keep going, right? Saying like, well, you're shaving off $27 a month, right? So $27 times 12, so you are saving $320 a year, right? Which can cover cell phone or bills or whatever, right? And you go, oh yeah, I can definitely do 94. So remember how I said it's a win-win-win-win-win situation? It's doable for you to get the car you liked, you wanted, right? The dealership sold the car, so they also win, right? Because they make money to feed their families. And the bank won as well. Why did the bank win? Well, remember your old loan? How much did you have to pay back the old loan? $7,328. And now you're giving extra $600 to the bank because your loan is extra, is stretched for extra 2 years. So bank is gonna make extra $600. Dealership is selling the car, so they're making the money. You are getting into the situation where you can afford, right? Because now it's less than 100, let's say, and so on. So now obviously you are locked in for 7 years rather than 5, rather than 3. But the shorter the term, more money you have to pay. So there's a lot of stuff, right, that goes into this finance, and I think that this is the coolest way to learn these exponential functions. So compounding, right, with this formula without e is the one that corresponds to our, what I would call vanilla exponential functions. And then you have the E function, right, which would compute the absolute maximum you could pay for this. Now you can also go now and change this to 7 and see what would that number be, which would be again few dollars more than this, but it's not going to reach 8,000, right? So, you know, you can do those calculations, and this number E will be back with vengeance in every of our next sections, and it will completely dominate 3.5 and pretty much every course you ever take. Let's jump into today's differential equations. I don't have to go far. I just clicked the first thing, and here is the problem with these, right? How about previous problem? Okay, previous problem had trig in it. Fine. Right, but trig can be written as is as well. So here's more trig. Oh, this was a trig heavy section. Oh, there's E again, right? So it doesn't matter which course you click, right? Which course you go to, it is going to be filled with exponential functions because those are extremely important, very frequent. They model a lot of our world, and we'll see that in 3.5 when we do all of the word problems. Please keep watching the announcements. I found a way to post the exam in Canvas. So I am figuring that stuff out today, tomorrow, and I am hoping to post exam 2 as soon as possible. So a lot of you voted for exam to be obviously in 2 days. A lot of you also voted to have exam next week. So I am going to actually push it for next week because I have to, because my MATLAB keeps crashing, and I just had not two retakes. I had an exam and then a planned retake of the exam because more than half of the students couldn't use my MATLAB because it was crashing and not opening and not loading and so on. And they would send me the videos. It's not that you know they were making stuff up. Now also I received a lot of complaints from you guys that you can't log on and do your homework. Then they post over there that they are merging to bigger servers and their service gets to be interrupted all the time. So what I decided is to push the exam for the next week, exam 2. And in that exam 2, I'm trying to get it to work in Canvas. Your exam was ready for my MATLAB, but then we can just, and that's what we have for this. Now, to answer the question on quizzes is, no, the only reason why those quizzes are effective is because they are every day. The idea of the quiz is to get you to practice every day. It is completely useless and pointless to have those quizzes if you are able to do multiple quizzes on other days and so on. The reason why 90% of students are absolutely abysmally bad in mathematics is because they think that mathematics can be learned like other classes where you can just memorize a few things and show up and beast the exam, and then you can forget the stuff you learned. The quizzes are there to force you, if you want those points and you want those quizzes to be counted and so on, to force you to do the time management, right? And log on every day and learn every day, because small chunks of 20-30 minutes every day, right, for a week, that's going to be less than about 3 hours. And combined, 3 hours in 7 days. And what you learn from that experience is going to be way better than what you do when you waste 5 hours in one day. No one learns 5 hours in one shot. The brain shuts off after 2 hours, maybe 3 if you are super nerd. You are not able to you are not able to, I mean, you can be studying, but it's just waste of time because you're not retaining any information. Any study time in excess of 2 hours on a subject in a row is complete waste of time. So that's why it's a strong emphasis on these quizzes to be every day. They're open 18 hours a day. I do want you to sleep 6 hours. 6 hours is enough. So, you know, in those 18 hours, you should be able to squeeze out 30 minutes for a quiz. I mean, that's the way, yeah, so that's the way it goes. So that's for the quizzes. So I am also going to open up office hours, right? And we will talk about, you know, for those of you who log on, the office hours will be using Microsoft Teams, and you will receive an email to join the list, right? And then at scheduled times, you can log on and, you know, chat with me, ask any questions. On my end, it will be screen sharing, just like what you see in this video. And on your end, you will either have your face camera on or not. That depends on you. And then your Microsoft microphone is going to be on, obviously, so I can hear what you're saying. So that's going to be on Microsoft Teams, and just look for the email. I'm thinking to start those as soon as possible, so no later than Wednesday. I did the testing phase already, and now I just need to add all of the emails. I need to add them manually, and it's 150 students. So I'm dreading my life right there. But other than that, I think I am fully set. I tested it twice already, and had no interruptions, no issues. You guys are able to see everything I write. And then we'll just see. I mean, the only issue I'm going to have is, you know, if 30 people show up at the same time and then everyone is trying to get something done, that's going to be interesting. But I will try to have everything ready within 2 days so that we can chat. And in addition to the regular office hours, I was thinking to open up something on Friday, let's say Friday afternoon. So, or maybe even Friday at noon or something. Well, I'll figure that one out. Maybe I try and see which one works better. There is no way that I can, you know, schedule something that it's working for everyone and also works for me, because I also have other responsibilities. Obviously, you know, homeschooling kids and everything else. That's you know, that's for everyone the same who has kids. They're home, and it's very difficult for me also to teach because they are just running and ripping up the house upstairs if I'm not there. So it's just you know, this is not ideal, but you know, unfortunately our New Jersey government is terrible. That's what we are stuck with. So there we go. All right, so this is what we can, you know, this is what we have, and that's all. I'll see you all in 2 days, and look for announcements, look for homework on my MATLAB, announcements in Canvas, and look for the email to join Microsoft Teams for office hours. Bye.